Okay, so how can we find where the stagnation points are using complex numbers? So let's say we ask the same question as what we did for the real potential. Where are the stagnation point at the surface of the cylinder? So for this, we need to compute the velocity field at the surface of the cylinder. And that is easy to do. If we want to go from the complex potential to the velocity, we just take the derivative with respect to z. So dw dz is equal to, remember, the real part is going to be equal to the velocity in the x direction, and the imaginary part is going to be equal to minus the velocity in the y direction. And so that is going to be equal to, we simply take the derivative of this, so u exponential minus I alpha, minus this constant here divided by z squared, minus I gamma divided by 2 pi times I times 1 divided by z. And so where is the velocity 0 at the surface of the cylinder? So at the surface of the cylinder, z is equal to a exponential I theta. So that represents the entire surface of the cylinder. So the contribution of the uniform flow is here. A squared u exponential I alpha divided by z squared, which is going to be a squared exponential I theta squared. So the a squared is going to cancel, and I'm left with u exponential I theta divided by, so the a squared cancel, exponential 2I theta. And here the contribution of the irrotational vortex is I gamma. Alright, so here this is the equation that we have, and we want to find the thetas such that this here, which is the velocity or the conjugate of the velocity at the surface of the cylinder, is equal to 0. So I can simplify this relation a little bit. I'm going to multiply everything by exponential I theta. So I'm going to have u exponential minus alpha times exponential I theta. So this is going to be a plus theta. So here in the end, I'm going to have I theta minus alpha minus, here I have a u exponential I theta. If I multiply by exponential I theta here, I'm left with exponential 1 over exponential I theta. So that is so that would be I minus theta minus alpha. And here I'm just left with I gamma divided by 2 pi a, which I can put on the other side. So this is equal to I gamma divided by 2 pi a. Now here I'm going to remind you, this is very far, but, oh, sorry, there's an exponential here missing. That exponential I theta minus exponential minus I theta divided by 2I is equal to sine theta, right? So here, this term is equal to u times 2I sine of theta minus alpha, and that is equal to I gamma divided by 2 pi a. You see that the I cancel here, and we are left with the same equation that determines the stagnation point of what we had before. So gamma is equal to 4 pi a u times sine of theta minus alpha. Note that last time when we did it for real potential, we did not have the minus alpha because we assumed alpha was equal to 0. Right, but so here this is the equation that we find that defines the stagnation points.